Good morning, students. In the previous class, that is class 1 of the chapter solution, I already completed the introduction part. What is the solution? Types of solution. Then what is vapor pressure? What is the solubility? Factors affecting solubility. Raoult's law. Then colligative property, different types of colligative property. Raoult's law. For a solution containing non-volatile solute, for a solution containing volatile solute, Henry law, application of Henry law. Today, that is class 2 of the chapter solution. I will try to complete elevation in a boiling point is a colligative property. Depression in a freezing point is a colligative property. And osmotic pressure is a colligative property. So before going to that one, let us recap. That is, what is a colligative property? It is the physical property of a dilute solution which depends upon the quantity of solute, the number of moles of solute species present in the solution, rather its nature. That is structure, composition, behavior. Then it is known as colligative property. Suitable examples of colligative property are: point 1, relative lowering in vapor pressure, RLVP. Point 2, elevation in boiling point. Point 3, depression in freezing point. Point 4, osmotic pressure. So first one is completed, that is a relative lowering in vapor pressure. So what is the formula? That is P0 minus PS by P0 is equal to mole fraction of solute. If we apply this formula, that is P0 minus PS by P0 is equal to N2 by N1 plus N2. For a dilute solution, neglecting this one, so P0 minus PS by P0 is equal to N2 by N1, where N2 is the number of moles, N2 is the number of moles of the solute, N1 is the number of moles of the solvent. So let us apply this concept of solving one problem. One problem is vapor pressure of water at 298 Kelvin is 19.2 mm. And the lowering in vapor pressure of a sugar solution is 2.03 mm. Calculate. Point 1, relative lowering in vapor pressure. Point 2, vapor pressure of solution. Point 3, that is mole fraction of water. It is known as solvent. This is the question. So what is the question? Mark that. Vapor pressure of a pure water at 298 Kelvin is given. Vapor pressure is given. And a difference in vapor pressure, lowering the vapor pressure of a sugar solution is given. Mark that. We have to calculate RLVP, relative lowering vapor pressure, and vapor pressure of the solution. mole fraction of the solvent, that is water. How one is solved? Mark that. Mark that from the question given that what are the data given? That is a P naught is given. P naught given. That is 19.2 mm. Lowering vapor pressure P naught minus PS is given. That is 2.03 mm. Mark that if P naught is given, P naught minus PS is given, then one is able to calculate PS. PS means vapor pressure of the solution can be calculated. How? That is P naught minus PS. P naught minus PS from this one minus or PS vapor pressure of the solution. How we calculate? PS is equal to P naught minus PS. Mark that. P naught, that is given. Lowering vapor pressure P naught minus PS is given, cancelling, that is PS. So from these two data, differentiating these two data, one is able to calculate the vapor pressure of the solution. So vapor pressure of the solution can be calculated. Next we calculate a relative lowering vapor pressure. Relative lowering vapor pressure formula is P naught minus PS by P naught. So P naught minus PS is given. P naught is given. So P naught minus PS by P naught. This value is given. By dividing this one is able to calculate the relative lowering vapor pressure. Next is mole fraction of solvent. So this value is known, this value is known, division also, that is RLVP is known. This value is equal to mole fraction of the solute. We know that. We know that for a binary solution, mole fraction of solute plus mole fraction of solvent is equal to 1. That means our aim is to calculate a mole fraction of solvent. That is mole fraction of solvent or mole fraction of water is equal to 1 minus mole fraction of solute. Mole fraction of solute calculated from this value. So 1 minus that value give rise to mole fraction of solvent or mole fraction of water. So in this way, one is able to solve a problem relating to relative lowering in vapor pressure. Next, switch over to the second colligative property, that is elevation in boiling point. Before going to the elevation in boiling point, it is necessary to discuss what is boiling point. Boiling point. Boiling point of a solution is defined as the temperature. It is the temperature at which liquid starts to boil. In other words, the liquid form and gaseous form possess same atmospheric pressure. I repeat again. It is the temperature at which liquid form and gaseous form coexist. That is, they possess same atmospheric pressure. It has been observed that the boiling point of a solution is somewhat higher than that of a pure solvent. This increase in temperature is known as elevation in boiling point. That is, increase in boiling point. Now, what is the reason why boiling point of a solution is elevated? Normally, we know that vapor pressure of a solution is lower than that of a pure solvent. I repeat again. We know that vapor pressure of a solution is lower than that of a pure solvent. And we know that boiling point is the temperature at which liquid form liquid form and vapor form possess same atmospheric pressure. That's why it is necessary to increase the temperature, as a result of which the vapor pressure graph of the solution must be increases. That's why boiling point of a solution always higher than that of a pure solvent. Now we have to plot a graph by taking boiling point, that is vapor pressure versus temperature. Graphical representation. Graphical representation. Mark that. If we plot a graph by taking vapor pressure versus a temperature, then we observe that, mark the graph. It is known as the atmospheric pressure. So it is known as this one. It is known as T2, it is known as T1. The difference in temperature known as del Tv. So this graph is for pure solvent. This curve is for solution. So mark that. If we plot a graph by taking vapor pressure versus temperature, we have this curve. It is clear that T2 is the boiling point of the solution and T1 is the boiling point of the pure solvent. From this it is clear that boiling point of a solution is higher than that of the pure solvent. So what is the increase in boiling point? That is known as elevation in boiling point. That is elevation in boiling point. That is T2 minus T1 is equal to del Tb. What is del Tb? Del Tb is known as increase in boiling point, elevation in boiling point. It has been observed that this elevation in boiling point of a dilute solution containing non-volatile solute is directly proportional to its molality. That is, what is molality? Now that is number of moles of non-volatile solute dissolved per 1 kg of the solvent. I repeat again. It has been observed that this elevation in boiling point directly proportional to the molality, or del Tb is equal to a proportionally constant Kb into molality. Equation 1. Where Kb is a proportionally constant known as molal elevation constant, or ebullioscopic constant. Mark that. What is the relationship? Del Tb is equal to Kb into molality. That means from this relation one is able to calculate the definition, derive the definition for ebullioscopic constant or molar elevation constant. Mark that. If the molality of the solution is 1, then Kb is equal to del Tb. Hence, the molar elevation constant or ebullioscopic constant is defined as the elevation in boiling point. I repeat again. The molar elevation constant or ebullioscopic constant is defined as the elevation in boiling point when molality of the solution is unity. That is, 1 mole of non-volatile solute dissolved in 1 kg or 1000 gram of the solvent. Then we have to prove that relation, how the del Tb is equal to Kb into molality. Derivation of the expression. Del Tb is equal to Kb into molality. We have to derive this relationship. Mark that. It has been known that two relation is there. That is del P proportional to del Tb, equation 1. Point 2. That is del P proportional to mole fraction of solute. Mark that, the relationship. It has been observed that greater the lowering in vapor pressure, mark that, greater the lowering in vapor pressure, higher is the elevation in boiling point. This is relation 1 indicates that greater the lowering in vapor pressure, higher is the elevation in boiling point. And also from Raoult's law we know that the lowering in vapor pressure, the lowering in vapor pressure is directly proportional. Relative lowering in vapor pressure of a dilute solution containing non-volatile solute directly proportional to mole fraction of the solute. So from these two expressions, one can be able to write that del Tb from equation 1 and 2 give rise to mole fraction of solute, or del Tb is equal to a proportional constant K into mole fraction of solute. Mark that. Now K is a proportionally constant, so del Tb elevation in boiling point K into mole fraction of solute. We know that if N1 is the number of moles of solvent while N2 is the number of moles of solute, then mathematical expression for mole fraction of solute, that is mole fraction of solute is equal to N2 by N1 plus N2. And for a dilute solution, neglecting N2, we have for a dilute solution, mole fraction of solute is equal to N2 by N1. We know that if W1 is the amount of solvent having molecular mass M1, then the above equation becomes mole fraction of solute is equal to N2 by W1 by M1. So putting this value of mole fraction of solute in this equation we have, that is del Tb is equal to K into N2 by W1 into M1. Mark that. If W1, that is amount of solvent, if W1, that is quantity of solvent, is 1 kg or 1000 gram, then we observe that this value is known as molality. That means del Tb is equal to K into M1 into molality. Mark that. M1 is the molecular mass for a particular solvent, its molecular mass remain constant. So constant into another constant is a constant, or del Tb is equal to Kb into M dash. It is the required expression. That means elevation in boiling point is equal to the proportionally constant, that is molar elevation constant into molality. So from this expression also it is clear that the elevation in boiling point depends upon the molality. The elevation in boiling point depends upon the number of moles of solute present in a solvent, but not its nature. Hence it is clear that elevation in boiling point is a colligative property. Next, from this we have to deduce an expression for calculating molecular mass. An expression for calculating molecular mass. Mark that. If we put this value of molality, we have, that is del Tb is equal to Kb into W1 into 1000 by M1 into V. That is volume of the solution. That is M1 into W2. That is number. What is molality? I repeat again. What is molality? Number of moles of solute. So it is W2 by M2 into W1, where M2 is known as the molecular mass of a non-volatile solute. So from this expression, M2 is equal to Kb into W2 into 1000 divided by del Tb into W1. If all other factors are given, if elevation in boiling point is given, that is weight of solvent is given, that is Molar elevation constant value is given, weight of solute is given. If all the factors are given, then molecular mass of a non-volatile solute can be calculated. So let us apply this formula to solve one problem relating to the elevation in boiling point. One question is there. Question 0.1 molar solution of a substance, 0.1 molar solution of a substance, it is formula del Tb is equal to Kb into molality, elevated, boils at 100.52 degrees Celsius. Calculate the molar elevation constant. Answer. Mark that what are the data given? Molality of the solution given 0.1 m and del Tb, that is elevation in boiling point, that is 100.52 minus 100 is equal to 0.52 degrees Celsius. This is given. Therefore, Kb, we know Kb is equal to del Tb by molality. So 0.52 degrees Celsius by 0.1 molality. Solving this one, degree centigrade by molality, one is able to calculate. Mark that. Molar solution is that molality of the solution is given and the boiling point is given, that is increase in boiling point, elevation in boiling point, increase in boiling point is given. So in that is change in boiling point. We know that boiling point of water is 100 degrees centigrade. So change in boiling point is equal to this much. And the relation from this relation, this value given, this value is given. By applying this formula, one is able to calculate the molar elevation constant or ebullioscopic constant. Next we discuss, another term is depression in the freezing point. Before going to the depression freezing point, better it is to discuss first what is freezing point. Next is freezing point. What do you mean by freezing point? Freezing point of a substance is defined as the temperature at which the liquid form and the solid form coexist. That means they have same atmospheric form, they remain in equilibrium. It has been observed that the depression, that is boiling point of it has been observed that the freezing point of a solution is lower than that of a pure solvent. I repeat again. The freezing point of a solution is lower than that of a pure solvent. That decrease in temperature known as depression in freezing point. So why freezing point of a solution is lower? We know that the vapor pressure of a solution is lower than that of a pure solvent. The vapor pressure of a solution is lower than that of a pure solvent. And we know freezing point is the temperature at which the solid and liquid possess same atmospheric pressure. That's why it is necessary to decrease, lower down the temperature. As a result, liquid form and solid form possess same atmospheric pressure. That's why the freezing point of a solution is always lower than that of a pure solvent. Next, we discuss this one in the form of a vapor pressure graph. Mark that. Vapor pressure versus temperature graph. Mark that. If a graph is plotted by taking vapor pressure versus temperature, mark that the nature of the curve is this one. So it is one curve, it is one line. It is known as liquid solvent, pure solvent. It is a solid solvent, it is a liquid solution. So this is the temperature, that is T naught. It is the temperature at which a pure liquid solvent solidify. And it is the T1 is the temperature at which a solution is solidify. So from this graph it is clear that the freezing point of a solution, is lower than that of a pure solvent. So this is the lower in temperature, that is known as delta F. So it has been found that the depression in freezing point delta F is directly proportional to molality of the solution. Or if you remove the proportion sign, delta F, a proportional constant Kf into molality, where Kf is a proportionally constant which is known as molal depression constant, or cryoscopic constant. Mark that. Now we have to deduce an expression for molar depression constant or cryoscopic constant. Mark that. If the molality of the solution is unity, then molar depression constant is equal to depression in freezing point. Hence, molar depression constant or cryoscopic constant is defined as the depression in freezing point when molality of the solution is unity. That is, 1 mole of solute, 1 mole of non-volatile solute dissolved in 1000 gram or 1 kg of the solvent. Now, next we have to deduce a mathematical expression. Mark that. What is the mathematical form? Delta F is equal to Kf into molality. Like elevation in boiling point also, by the same principle, one is able to prove that delta F is equal to Kf into molality. By putting the value of molality, we know that is molality is equal to number of moles W2 into 1000 by M2 into W1. Putting this value here, we have, that is delta F is equal to Kf into W2 into 1000 by M2 into W1. Our aim to derive an expression for calculating the molecular mass. The molecular mass of the non-volatile solute is equal to Kf into W2 into 1000 divided by delta F into W1. Mark that. If all the factors are given, then one is able to calculate the molecular mass of the non-volatile solute. And also mark that From this expression it is clear that the depression in freezing point, of a solution containing non-volatile solute depends upon the molality, that is the number of moles of solute, that is quantity of solute present in the solvent, but not its nature. Hence it is clear that the depression in freezing point is a colligative property. Now we solve one or two problems basing upon this formula. Question: 34.2 gram of a sugar solution, that is C12H22O11. 34.2 gram of a sugar solution freezes at minus 0.372 degrees Celsius. Calculate the cryoscopic constant. Calculate the value of cryoscopic constant. Answer. Mark that. What are the data given? That is del TF is equal to 0 minus 0.372 is equal to 0.372 degrees Celsius. Del TF given. Then that is present 32 gram of a sugar solution. 32 gram of a sugar solution present. 32 gram of a sugar solution present in 500 ml. Freezes are this one. That means if 500 ml, 500 cc sugar quantity is then this one, then for 1000 cc, the quantity of sugar is equal to 34.2 into 2, that is 68.4 gram. So that means 68.4 gram of sugar present in 1000 cc of water or 1000 gram of water. Hence, one is able to calculate the molality. Molality is equal to weight 68.4 by molecular mass of sugar, that is 342. That means one is able to divide this one is able to calculate the molality. So molality calculated, the depression in freezing point is calculated. That means the depression in freezing point, that is cryoscopic constant, is equal to del TF by molality. This value is known, by simply dividing this one is able to calculate the depression in freezing point or cryoscopic constant value. Next we switch over to the third colligative property, that is osmotic pressure. Before going to the osmotic pressure, it is necessary to discuss a term, what is osmosis. What do you mean by osmosis? It is the spontaneous flow of a solvent molecule. Osmosis is defined as the spontaneous flow of a solvent molecule from solvent towards solution, or from solution of lower concentration to a solution of higher concentration when both are separated by a semi-permeable membrane. I repeat again. That is, osmosis is a spontaneous flow of a solvent molecule from solvent to solution, or a solution of lower concentration to a solution of higher concentration when both are separated by a semi-permeable membrane. What is semi-permeable membrane? It is a special designed membrane. The small holes of this membrane is adjusted in such a way that it only allows the solvent molecules but not the solute molecule. Next, another one term is known as, that is osmotic pressure. Next is osmotic pressure. What do you mean by osmotic pressure? The excess pressure developed on the solution side to check the flow of solvent from solvent to solution when both are separated by a semi-permeable membrane is known as osmotic pressure. I repeat again. The excess pressure must be developed in the solution side to check the flow of a solvent molecule from solvent to solution when both are separated by a semi-permeable membrane is known as osmotic pressure. If higher pressure is given on the solution side than the osmotic pressure, then there is a flow of a solvent molecule from solution towards solvent. I repeat again. If higher pressure than the osmotic pressure is given on the solution side, then there is a movement of solvent from solution towards the solvent. That is known as reverse osmosis. That term is known as reverse osmosis, which is the best application of, that is, desalination of seawater. That is removal of salt from seawater. That is known as reverse osmosis. What is reverse osmosis? That means if higher pressure is given than the osmotic pressure on the solution side, movement is reverse. That means solvent move from the solution side to solvent side. This is known as reverse osmosis, and it is most applicable in case of desalination of seawater. That is removal of salt from the seawater. Next, another two term is there. We know that if two solution possess same concentration, same osmotic pressure, then that is known as isotonic solution. Another term is there, that is isotonic solution. What is isotonic solution? I repeat again. The two solutions having same osmotic pressure and same concentration are known as isotonic solution. If not osmotic pressure remains same, then one is lower osmotic pressure, one is higher osmotic pressure. The solution possesses lower osmotic pressure known as hypotonic, and that one possesses higher osmotic pressure known as hypertonic. Another two term is there, that is hypotonic, and another is known as hypertonic. Mark that. If the two solutions have not same osmotic pressure, then one possesses lower osmotic pressure, one possesses higher osmotic pressure. The solution which possesses lower osmotic pressure known as hypotonic, while another one possesses higher osmotic pressure is known as hypertonic solution. Next we discuss Van 't Hoff theory of dilute solution. Van 't Hoff theory of dilute solution is made up by combining two laws. One is known as Boyle's Van 't Hoff law and one is known as Charles Van 't Hoff law. Next we discuss Van 't Hoff Boyle's law. Van der Waals law or Boyle's Van der Waals law. Mathematical expression is pi proportional to C at constant temperature. This law states that the osmotic at constant temperature remaining constant, the osmotic pressure of a dilute solution directly proportional to its concentration. Mathematically, pi is the osmotic pressure, C is the concentration, where temperature remaining constant. Next is Van der Waals law. Mathematical expression pi proportional to T, concentration remaining constant. Mark that. This law, Charles Van der law or Van der Waals law, states that concentration remaining constant, the osmotic pressure of a dilute solution is directly proportional to the temperature. I repeat again. This law says that the concentration remaining constant, the osmotic pressure of a dilute solution is directly proportional to the temperature. Next we discuss Van der theory of dilute solution. Next we discuss Van der theory of dilute solution. This is derived by taking the Van der Waals law and Van der Waals law. We know, according to Van der Waals law, pi proportional to C, temperature remaining constant. And according to Van der Waals law, pi proportional to T, concentration remaining constant. Combining these two laws, that is Boyle's Van der Waals law and Charles Van der Waals law, we have pi proportional to Ct. Or if we remove a proportional sign, we have to put an equal sign and a constant, or pi is equal to Crt. Equation 1. Where R is a proportionally constant, which is known as equivalent to universal gas constant. Its value may be 0.0821 liter atm per Kelvin per mole or 8.314 joule per Kelvin per mole. Where is C? C is known as the concentration. But we know concentration, that is the number of moles per unit volume. Putting the value here, we have pi is equal to N by V RT, or pi V is equal to nRT. It is equation 2, it is equation 3. Mark that. This is equation 3. Equation 3 is the required expression for osmotic pressure of a dilute solution. Mark that. From this expression also, we have to calculate another expression for calculating the molecular mass. Mark that. If we put, that is N, that is the number of moles, that is W2 by M2, weight of solute by molecular mass solute in this expression, we have pi V is equal to W2 by M2 RT, or we have to calculate the molecular mass of a non-volatile solute, that is M2 is equal to W2 RT by pi V. Equation 4. So it is the required expression for calculating the molecular mass of non-volatile solute from the osmotic pressure data. So if all the factors are given, then from this expression one is able to calculate the molecular mass of a non-volatile solute. Mark that. By applying this formula also, one is able, if osmotic pressure is given, volume is given, universal gas constant is given, the temperature given, weight of solute is given, if this data is given, then one is able to calculate the molecular mass of non-volatile solute. And another one thing, mark that, the expression is, what is the expression? That is pi is equal to CRT, or pi is equal to N by V RT, or NV, that is pi is equal to N by V RT, or pi V is equal to nRT. So from this expression, from this mathematical expression, it is also clear that osmotic pressure of a dilute solution depends upon the number of moles of the solute, non-volatile solute present in the solution, but not its nature. Hence, it is clear that osmotic pressure of a dilute solution is also a colligative property. So in this class, that is class 2 of the chapter solution, I completed what is colligative property. Under this, relative lowering vapor pressure is a colligative property. Elevation in boiling point is a colligative property. Depression in freezing point is a colligative property. And last one, osmotic pressure of a dilute solution is also a colligative property. It is all about the chapter solution.